The other way around is a difficult theorem. So, sufficiency. Okay. So, given S bounded and closed in R. And since it's bounded, we can find an interval that contains the whole shebang, right? Okay. Now, the Borel-Lebesgue condition says if I have any cover of S, I have to be able to reduce it to a finite subcover. All right. Given a collection of open sets, this can be a mighty big collection, right? Such that in their entirety, they contain S. Must extract finite subfamily. So I'm going to go in and find only finitely many of the O sub alphas that still cover S. If I do that, I will improve the theorem, right? This is the Borel-Lebesgue criterion. I have two things going for me, closedness and boundedness. I have an arbitrary cover, and I have to find this finite subfamily. Okay. So, what shall I do? What was that thing that worked for the boson wire stress thing? Method of bisection. Well, let's draw a picture again. There's the origin. Here's S spread out all over the place, but of course S is bounded and it's closed. So if there's any limit points laying around, they're in S, right? Okay. Well, now S is covered by all these bazillion open sets, right? They're just everywhere. I don't want to scroll and draw too much, right? There's open sets galore, spread all over the place. They're members of C, and their union covers S. It may not cover alpha beta, that's okay, but at least it covers S. Alpha beta is just limit, the fences on either side of S. Most assuredly, the union of all the open sets in the cover contains S. All right. Let's do our little trick. Let's split this thing in half again. So I find alpha plus beta over 2, and I go south and north, right? To the left and right of the midpoint of alpha and beta. Now, here's the argument. One or the other side must contain an infinite number of sets required to cover that half, right? Because if only finitely many of the open sets in C are required here, and only finitely many open sets are required here, then I only need finitely many, the union of two finite sets. The center point, of course, would be in one of these things is swapping around here. So everybody in S would be covered by finitely many of the sets in C, and that would mean Jesus is compatible, right? So let's assume that one or the other or both of these require infinitely many sets in C to do the job, to cover. Okay. Let's just, for the sake of definiteness, make that so. Now, we do it again. Cut that one in half. And let's suppose it's this one that requires infinitely many. You get the picture. This is work diffuse ops, method of bisection. So here we go. We keep cutting these, cut these, cut these. What do we have? A sequence of closed intervals that are nested by the intersection theorem. There's a common point, lambda. Is that lambda inside or outside S? S is closed, remember? Lambda is a limit point for S. So lambda had better be where? Inside S. Okay. Let's just blow this up here. So here's a blow up. Here's lambda. And, of course, these intervals were coming down on here. However, I don't want to draw too many or crap up my drawing. Okay, now, lambda was part of S, so one of the sets of C, or several, at least one, though guaranteed at least one, covered lambda, didn't it? Well, okay, there he is. This set here belongs to Gothic C. He was in the collection because lambda was covered. Lambda's in S, it had to be covered by somebody in C. All right. This thing has a certain size. You can go from lambda to this wall or lambda to this wall. Let's say the shortest distance there is epsilon. So the short side is epsilon. Okay? All right. These closed intervals, the norm is going to 0. Do you suppose that if we go far enough with our sequence of nested closed intervals, that the norm of one of these things would be less than the short side distance here, epsilon? What would that do? What would that do? It would put the infinite number of, remember there's an interval here. How did we get those intervals? We said that that interval is one that requires infinitely many sets in C to be covered. But wait, this guy does it. So that's not true, is it? You know, we keep making this argument, need infinitely many, need infinitely many, need infinitely many, need infinitely many. Oh no, we're so small that only one of them does it, right? One of them does it. So I didn't need infinitely many at some point. That's a contradiction, isn't it? That's a contradiction. And the contradiction means that only finitely many are required at the very outset. If you assume you can't reduce it to a finite subcover, then you track these things down, always insisting on needing infinitely many in each step. But then you get so small, that if you say, I still need infinitely many, there's one of the members of the cover has already got you covered there, the whole thing. That's one. That's one. So you violated the assumption there. The indirect proof assumption is that you're constantly requiring infinitely many sets in C to cover it, and there you only need one. Contradiction. Therefore, we only require finitely many to begin with, and that's the Heinemann law. Okay? He always claps for me. Does that make sense to you guys? It's an indirect proof. You keep chopping things in half until you get so small that one of your original cover members covers everything. That's your contradiction. Okay, well, just coming back to each other. Did you guys do that in analysis too? Or did you just sort of look at the result? You didn't do it. Didn't prove it. But you know what it is. Okay, good. I was just hoping this wasn't totally new stuff. not totally new, but you didn't prove it.
Right.
Okay. I believe in proving things.
Yeah.
I never believe things until I prove them. So now we
Did you
have,
ever do that one that we got stuck on last time?
no, I have to figure that out.